Hello, Algebra. We are on our next video lesson here, 6.3 exponential functions. So our main focus today is actually the graph of these exponential functions. So we've been working with exponential functions for the last few weeks, right? Remember, that's any function or equation where your variable is in the exponent. So like y equals 2 to the power of x. So do you guys see how our variable is the exponent? So I don't think we've really ever talked or thought about what would the graph look like, right? So if I'm going to take us back to our first page of notes here. So you guys have this. And if we look here on both of our charts and we took 2 to the power and 10 to the power of something, we notice, like, look how rapidly our numbers grow, or look how rapidly they decrease. And same thing with our tens, right? We're getting really, really big fast, or we're getting really, really small fast. So keep that in mind when you're thinking of what the graph visually would look like of these equations, okay? So if we come back to this page in our notes here, we have 4 graphs, right? I want you to pick, there's 2 of them that are representing exponential functions, okay? So I want you to go through, pause the video, and decide which ones you think are exponential functions. So keep in mind again, exponential functions grow really fast or they decrease really fast, okay? So pause the video and then I will go through it with you. Okay, did you pause the video? Did you try them all? Because here we go. Okay, so on this first graph here, it's actually doing both. It's decreasing as you move to the left, but once we hit 0, it increases really fast. But it's not just doing one, it's doing both. So this one is not exponential. We would actually call this one quadratic. And that's when you would have, like, your function would look like something to the power of 2. You don't need to write that, it's just kind of fun information. We'll get to that in probably a month or so. So that one is not exponential. This one over here, I hope you're thinking is, right? We're starting off pretty small, then all of a sudden we just start to go up, 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 up real quick. This would be called exponential growth because we're getting bigger. Yep, it's growing real fast, real rapidly, okay? Exponential growth. Okay, now this bottom left one, we're starting at a pretty large number, but then we're increasing or decreasing very rapidly. And eventually we'll just bottom line, flat line down here. That would be exponential decay. We're getting smaller. All right. And later on, not today, but later on in the week, we'll talk about what makes the difference between exponential growth and decay, like in your equation, like what's the difference, okay? And then I'm sure since you guys are smart students, I said there were 2 that were exponential. This one, just by process of elimination, is not exponential. This one's actually cubic. And the reason why it's cubic is because it does grow very rapidly and decrease very rapidly, but we have this little part where it kind of like levels out right here. So a cubic, this is just fun information, would be any function to the power of 3. So any number to the power of 3 will give you a graph that looks like this. Okay? So this is what our graphs will look like if we're working with exponential functions. They're going to grow really fast or they're going to decrease really fast. Okay? So this is what you're going to be kind of hopefully envisioning while you're working on our lesson today. So our first part's very simple. We've done this many, many times before. We're evaluating a function given a value. So let's see here. I could probably zoom in a little bit, I suppose. So it says evaluate the function at the given value. So this is just calculator work. We love calculator work. I zoomed in too much. Oh, that should be okay. So it says f of x equals 5 to the power of x. Do you guys notice how, again, our variable is in the exponent? That's a tall, like a sign that it's exponential. So we're just going to plug in 4. So f of 4 equals 5 to the power of 4. Now it's just in your calculator, folks. 5 up arrow, 4 equals 625. Perfect. That's it. 625. So if you were to graph that ordered pair, you plugged in 4 and you got out 625. That's what that would look like. Right? Quite large. Quite large. Okay, let's try another one. H of t equals 3 times 4 to the power of t. Again, do you guys notice how our variable is in the exponent's position? Excuse me, words are hard today. So we're going to plug in -3 for t. So 3 times 4 to the power of -3. Again, folks, calculator work, we love this. 3 times 4 to the power, parentheses, -3. And we're going to hit equals. And yes, decimals are okay for when we're graphing and when we have word problems because it just makes our lives a little easier. So we're going to have, let's see here, running out of space. This equals 0.04, should we do 69? Go to 4 decimal places, that's probably pretty accurate. So again, we plugged in -3 and we got out 0.0469. And then our last one, folks, of this type of example, we have y equals 8 times 0.7 to the power of x. And one last time, I'm going to say it. Do you guys notice how our variable is in the exponent spot? So it's exponential. So let's plug in 8 times 0.7 to the power of 3. And we're going to type it in our calculator. 8 times 0.0, I lied, 0.7 to the power of 3. So we're getting 2.744. So again, we plugged in 3 and our output was 2.744. Okay. So that's kind of like example 1, level 1. We just plugged in and got an answer out. Level 2 would be given kind of a word problem, an application of this, and getting out our answer. All right. So it says an initial population of 20 rabbits triples every half year. The function f of x equals 20 times 3 to the power of x gives the population after x half year periods. How many rabbits will there be after 3 years? Now, don't get ahead of me here. I know we're kind of in the mode right now. We just plug in for our variable, which you're not wrong. But you have to be careful because it says x represents half year periods. Half year periods. So you're not just plugging in 3 because that's 3 years. We have to figure out how many half year periods are in 3. Well, how many half years are in 1 year? Well, there's 2, right? 2 half years in 1 year, and we have 3 years. So 2 times 3 equals 6. So we're really plugging in 6 into our function. Okay, so let's plug in 6. Okay, so again, go back to your calculator. We're typing in 20 times 3 to the power, use that up arrow, of 6. Anyone have a guess? So remember, this is how many bunnies will there be after 3 years if we started with 20? A ton. There's a ton. 14,580. That's a lot to happen in just 3 years. Make sure we label it because it is a word problem. We have a unit. So again, you guys, after 3 years, we started with 20 rabbits and we ended up with almost 15,000. That's bonkers. It's a lot. Okay? We'll do more of these at the end of the week. I think you guys will like them. Exponential growth and decay are fun problems to work on. All right, now our last 3 examples here, we're just graphing. It says graph the function, then determine if it's exponential or not. So my hope is by just looking at our equation, we're going to be able to tell if it's exponential or not right away. Okay? So if we look here, this is kind of a review. We've actually seen problems like this before. I hope you're noticing that our variable isn't in an exponent, right? So this isn't going to be exponential. I hope you're thinking this is linear, right? We've done this. We did this for a long time. So we know we have to plug in our 5 values into our t-chart. I'm just going to start off like this real quick. We're going to plug them all in. And we'll crunch them out in our calculator, okay? So we're going to plug in our 5 values into our equation. Here we go. Again, it's just calculator work. Plug them in exactly how you see it. 3 times negative 2 minus 4. Negative 10. 3 times negative 1 minus 4. Negative 7. 3 times 0 minus 4. Negative 4. 3 times 1 minus 4 equals negative 1. And our last one, 3 times 2 minus 4 is 2. Okay, so if we graph these, we plugged in negative 2, got out negative 10. So let's plot that point. Left 2, down 10. Put a big old dot there. Negative 1, 7. Negative 1, negative 7. Left 1, down 7. Zero, negative 4. Nope, this one should be down one more. My fault. I can't count to 10. 1, negative 1. 2, 2. We should be getting a line, folks, right? And I hope you would have realized that right away. Our M is 3. Our B is negative 4. This is a good review problem. Start at negative 4, go up 3 over 1, up 3 over 1, up 3 over 1. We did that plenty and plenty of times so far this year. So no, this one is not exponential. It's linear. It's just a line. Okay. Our next one. If we just look at our graph or our equation, yes, you're noticing it. Our exponent has a variable. So this one will be exponential. Good news, we start off the same way we always have. Plug in our 5 values. So 2 to the negative 2, 2 to the negative 1, 2 to the 0 power, 2 to the first, 2 squared. Again, folks, calculator work. 2 to the power of negative 2. Decimals are okay when we're graphing. That's okay. 2 to the power of negative 1, 0.5. What's anything to the 0 power, you guys? 1. 2 to the power of 1 should just give us a big old 2. And 2 squared, 2 times 2 is 4. All right, let's graph it. So again, we plugged in negative 2, got out 0.25. So you're going to have to eyeball. These graphs aren't very user-friendly for this kind of a problem. So I'm just going to go barely above the x-axis. Okay. Same thing for negative 1, going up a half, just a little above that last one. Plugged in 0, not negative 0, just 0, goodness. And I got out 1. Plugged in 1, got out 2. Do you guys see how it's growing? Plugged in 2, got out 4. Should we go do a few more? We can do one more, otherwise we will run out of space. If we plug in 3, we should get out 8. 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8. So it is growing exponentially. Yes. Woo! Look at that. Exponential growth. Just like your guys' learning this year, you're growing exponentially, right? Okay, I'm almost done. I'm sorry. All right, last one here, folks. So if you look at the front of our notes from today, I said something about if you have a 2 as your power, it's called quadratic. That was our first example, and it's going to kind of look like a U when we're done. So let's practice doing that. So again, plug in our 5 values. So I'm going to take -2 to the power of 2. And it has to be in parentheses, otherwise that negative is going to mess everything up. -1 to the power of 2. 0 to the power of 2. 1 to the power of 2. And 2 to the power of 2. So again, take out your calculator. We're plugging in parentheses -2 and parentheses to the power of -2. Oh, I'm lied. Messing myself up. 2 is 4. Again, -1 to the power of 2 is just 1. 0 to the power of 2, goose egg, 0. 1 to the power of 2 is 1. And 2 to the power of 2, 2 times 2 is 4. So when we graph this one, -2 up 4, we'll notice there's some symmetry because whenever you take a negative number and square it, you get the same answer as its positive counterpart, which is kind of neat. That's why it makes that U shape, because it doesn't matter if it's positive or negative, you get out the same answer. So it's like you can reflect your graph over that Y axis. It's pretty neat. It's pretty neat. Okay, good work. Thank you for watching. Let me know when you're done with the video lesson and I will get you started on your homework.